In this lecture, we'll have a look at non-stationary time series models and some concepts related to non-stationary models. Remember that a time series is stationary if the expected value of each yt is constant, the variance of each sample point is constant, and the covariance between yt and yt minus s cannot depend on t. It can depend on s. Now, a very simple and nice model to consider when we want to look at the stationarity concept is the AR1 process. And remember, we say that yt follows an AR1 process. If I can write it as beta 1 plus rho times the lagged value of y plus some error term epsilon t, then it follows an AR1 process. Because in this case, we know that a necessary condition for stationarity is that rho must belong to -1 to 1, what we call the stability condition. If the error terms are white noise and this stability condition is satisfied and we start off yt in the correct way, then the yt time series will be stationary. However, if rho is equal to 1 or rho is greater than 1, or if rho is -1 or less than -1, then for sure it cannot be stationary. If rho is equal to 1, the variance of yt will keep on increasing with time, going to infinity as t increases. In the AR1 process, if rho is equal to 1, then we know that the process is non-stationary. If rho is just slightly less than 1, then the stability condition is satisfied and the process can be stationary. Therefore, this particular value of rho, that is rho is equal to 1, is of great importance. It is sort of the cutoff point between non-stationarity and stationarity. So if it's the case that rho is equal to 1, beta 1 is equal to 0, and the error terms are white noise, then we will call this AR1 process a random walk. So to summarize this, a random walk process is a process where the error terms are all white noise. Then the process yt equal to yt minus 1 plus epsilon t is called a random walk. Note that this is indeed a special case of the AR1 process where beta 1 is 0 and rho is equal to 1. So let's just have a comparison between two AR1 processes. In one case, rho will be 1 and it's a random walk, and in one case, rho will be slightly less than 1. So here I have a picture with time on the x-axis, the y observations on the y-axis. I have marked out time t minus 1 and t, and I have a particular value for yt minus 1. I want to consider two cases. In one case, we have a random walk, so yt is equal to yt minus 1 plus epsilon t. In the second case, we have a stable AR1 process where beta 1 is 0, so in that case rho is less than 1, perhaps 0.99 or something. Doesn't matter as long as it's less than 1. Epsilon t is a white noise process, so the expected value of epsilon t is 0. If you look at the random walk model, it says that y in period t is equal to whatever value it was in t minus 1 plus a random error term which has an expected value of 0. So the expected value of yt with the random walk is the same as the value in t minus 1. So we can expect the random walk to go horizontally when t increases by 1 unit. Of course, it will not go exactly horizontally because we have to add an error term, but this error term has an expected value of 0. So it means that it's equally likely to go slightly up or slightly down. On the other hand, if we look at the stable AR1 process, it says that y in period t is equal to rho times whatever value it was in t minus 1 let's say that the rho is 0.9. So that would mean that y in period t is 90% of the value in t minus 1. That means that 90% means that it goes towards 0. Now this is the expected value of yt. We also have the error term in this case, but again, this has an expected value of 0. So the error term can take us a little bit above this value or a little bit below this value. So we can go here or we can go here. But on average, the yt will decrease. So the important difference between the stable AR1 process is that there is always a tendency for this process to be pulled towards the x-axis. There is what we call a mean reversion, a tendency for the process to revert to its mean, which for the stable AR1 process is 0. For the random walk process, on the other hand, there is no mean reversion, and that is the key difference between the stable case and the non-stable case. So this is also a reason for why the process is called a random walk. If you imagine this dot being a person observed from above, and this person is walking to the right, then on average this person will walk horizontally, but due to this random error term, the walk is really random. It could be slightly to the left or slightly to the right. So let's have a look at time series data which follows a random walk. Here I have time in the D column. I have the error term in the E column, and that's simulated such that it's white noise. You can see that here the standard deviation of each error term is 0.2. I have set beta 1 to 0 and rho equal to 1, which is the necessary condition for the process to be a random walk. In this case, I actually start the process at 0. So y0 is 0. Then the next one, y1, is just equal to y0 plus the error term, as you can see. The error term in t equal to 1 is minus 0.17, and that's also the value for y1. F9ing a couple of times, we see that there is in general absolutely no tendency for this process to revert to 0. Each time t increases by 1 unit, there is a 50-50 chance that we will go upwards or downwards. A couple of random walks. So with the random walk process, as long as we start the process at y0 equal to 0, then the expected value of yt will be 0, right? Because the expected value of y1 will be the expected value of y0 plus epsilon t, both are 0, and so on. So the expected value of each yt is 0. However, if I look at the AR1 process where the rho parameter is 1, but where beta 1 is not 0, then it looks like this. And if we set y0 equal to 0, we can see that expected value of y1 is then beta 1 plus expected value of y0, 0 plus 0. So the expected value of y1 is now beta 1. Similarly, the expected value of y2 will be beta 1 plus the expected value of y1, which is beta 1 plus 0. So that will be 2 beta 1. If you keep on doing that, you can see that the expected value of yt is actually t times beta 1. So this process will have a drift that depends on beta 1, and that's why we call this a random walk with drift. So that's the process. If yt is beta 1 plus yt minus 1 plus epsilon t, then it's called a random walk with drift. Naturally, it's only if beta 1 is different from 0 that we have a drift. If beta 1 is 0, then we revert to the standard random walk. We can easily see this drift if we do a simulation. Let's change the drift parameter beta 1 to 0.1, and we can see clearly that there is a drift upwards in the random walk process now. The expected value of yt is now 0.1 times t. So the expected value of y100, for example, is 10. Similarly, if I make this negative, there will be a drift downwards. So if we set it to minus 0.1, there is a corresponding drift downwards. So to even more strongly emphasize the importance of this rho parameter being equal to 1 or not being equal to 1, we introduce one more concept called the unit root. The terminology we use is that we say that the AR1 process has a unit root if rho is precisely equal to 1. Remember, we concluded that when rho is equal to 1, the stability condition is not satisfied and the process simply cannot be stationary. So an AR1 process with a unit root is certainly non-stationary. Another way of expressing this is that a random walk is simply an AR1 process with a unit root. It's a pure random walk if beta 1 is 1, and it's a random walk with drift if beta 1 is different from 1. The next important concept that I want to introduce is the concept of difference stationarity. So we start with an arbitrary time series process. If it turns out that the first difference of this time series is stationary, then we call it difference stationary. Remember that this delta yt, called the first difference, is simply defined as yt minus 1. Yt being the value in this period, yt minus 1 being the value in the previous period, delta yt is simply the increase in yt from the previous period to this period. If delta yt is negative, that means that we have a decrease. So consider, for example, the pure random walk, the one without the drift, in which yt is equal to yt minus 1 plus epsilon t. We know that this is a non-stationary process because it has a unit root. However, by just moving this on the other side, we see that yt minus 1 is epsilon t. And this is precisely the delta yt. So we have delta yt is equal to the error term. The change in yt is the error term. And since this is white noise, this is white noise, and delta yt is stationary. So from this we can conclude that a random walk is difference stationary. It's not stationary, but it is difference stationary. One more related concept is the concept of being integrated of order 1. The definition is that a process is integrated of order 1. We use the notation I parenthesis 1. The requirement for a process to be I1 is that it's not stationary, but it is difference stationary. The prime example of an I1 process is the random walk. It is not stationary in itself, but when you take the first difference, you get a stationary process. So the concept is really closely related to being difference stationary. The only difference is that there is no requirement for a process to be non-stationary in order to be difference stationary, as there is for I1. If you look at this process, for example, 0.5 yt minus 1 plus epsilon t, it satisfies the stability condition, so if we just start it out correctly, it can be stationary. Then it's not an I1 process. However, it will be difference stationary. If you look at the delta yt, which is yt minus 1, that is 0.5 yt minus 1 plus epsilon t minus yt minus 1, and 0.5 minus 1 is minus 0.5. So it still satisfies the stability condition, so it is actually difference stationary as well. The final concept we will talk about in this lecture is the concept of being trend stationary. So a process is trend stationary if there exists a beta such that yt minus beta t is stationary. For example, if there is just a linear trend in the yt time series, so if yt is equal to beta 1 plus beta 2 times t, that is yt increases or decreases if beta 2 is negative linearly with time with an error term like this. So yt will be something like this, beta 1, slope beta 2, and to that we need to add an error term, so yt may look something like this. Then it's not stationary because the expected value increases over time, but it will be different stationary. And that's simply because yt minus beta 2t is beta 1 plus epsilon t, and since this is white noise, this whole thing is stationary. An important econometric problem is to distinguish between trend stationarity and different stationarity. And this is a topic that we will discuss more a little bit later.